Okay, before we begin, can everyone hear me on Zoom? Okay, thank you, Ian. I'm gonna enable this. Okay, so we can go ahead and begin. Welcome back. Happy Wednesday. And this will be our official last lecture of the semester. So we're in week 14 currently, and today we're going to wrap up chapter 5. And we're going to talk about the ICMP protocol and how we can have some sort of configuration over the given network. Um, Last assignment that is to do is assignment 3, which was already out a long time ago, and that is going to be due November 23rd. That is going to be this upcoming Sunday. So just be aware of that. And then our final exam will be here. I think you can already see the exam, but it will be locked on your end, and you cannot view it until that next Monday, which is the 24th. So you have a whole day to complete it. And then next Wednesday, it's completely off for Thanksgiving. And then the next week after that is nothing due. There's one thing I want to emphasize is just, and I might have bugged the students over and over about this, but to complete the SPIs, and that would be highly appreciated and very recommended for the students to do that. And there's extra credits that I have announced as with it and the announcements regarding the SPIs. So I think to complete it, it's very straightforward. I think you log into UCF, it should already prompt you to do your SPIs for all your courses, not just mine. Okay, so that is that. Does anyone have any questions, any concerns, anything they want to ask before we start our lecture? Okay, good. No, just give me one moment. Okay. Okay, so as usual, the lecture, some of the slides are borrowed from the book, so you can use that link to get to them. And so the roadmap or where we are right now, last class we talked about software-defined networking and we talked about the control plane of part of the software-defined networking. Today we'll talk about ICMP. And so ICMP is going to be it shifts from the routing algorithms and jumps to like control and error messages. So that prepares us. The ICMP is going to prepare us to understand how diagnostic issues and test basic connectivity happens. Okay, so ICMP just stands for Internet Control Message Protocol, and it's the communication at the network level. So this is how hosts and routers communicate with each other and share problems or information in the network so devices know why packets have failed. So it does not have to do anything with data transmission. It does not have anything to do with TCP or UDP. Okay, so one of the major role of ICMP is going to be error reporting. When something goes wrong with delivering packets, it tells a host or a network that it cannot be reached, or when a port or protocol is not available. That was hectic, right? To get to the class? Yeah. Yeah. I think they have an exam or something outside. So ICMP is going to support echo request and reply. Echo maybe by the by the network admins, and then a reply by the actual device itself, and to see if the device is pingable or how long it takes to respond. Now, ICMP, to keep in mind, is also considered as a network layer above IP. So even though its message is right inside the IP packets, this means IP handles the delivery of ICMP messages, but routers treat ICMP messages as like a core part of the network layer works. So the layered relationship lets the ICMP report problems about IP while depending on IP to vary the message. So every ICMP message includes going to be a type, a code, and a description, as you see on the right-hand table. And this is basically is going to give identifications or identifiers about the original packet that was triggered. So the report lets the receiver know what's going on when what went wrong. And the general category or the type describes here, as you can see, we have 0 to 12. This is going to give the reason within that category so the system can identify the exact issue. Okay. The table here shows some common ICMP messages used for diagnostic and routing behavior. So for example, we have type 0 and code 0 here. This is just going to be an echo reply. This is sent back during a ping. Type 3 here is going to be has code 1, and that indicates different unreachable errors or different unreachable hosts, maybe protocols or unreachable port. So that is something that is being unreachable. Type 11 here we have which is usual where the time to live has expired. And this is used by traceroute to map each hop. We'll talk about the difference between ping and traceroute as well. Type 12 here has code 0, indicates there's a bad IP header and tells the receiving device the original packet was malformed. So traceroute and ICMP, right? So we want to differentiate between those, and we want to know if they work together or are they different. So traceroute works by discovering each router on the path between the source and destination. Ping only just pings a host to make sure that it's reachable or not. So a typical, maybe you can say flow or diagram for a given traceroute is going to be usually the host that is pinging the destination, and there's a traceroute, which is basically usually going to be a number of hops that it's going to be that takes the original message or the original ping message, and it shows the overall path. So first thing that it does is the source begins by sending a set of UDP probes, and probes is going to be basically the packets that are sending towards the destination. So each probe in the first set has a time to live of 1, which means the packet is only allowed to reach the first router before expiring. And then traceroute repeats this with multiple probes to get consistent timing. And a second probe is going to be sent out that has a time live of 2, which allows these packets to reach the second router before expiring. So we use incremental time to live values that lets the traceroute map each hop in order. So it would increase to 3, 4, depending on the hops. And then every hop sends back an ICMP message when the time to live reaches 0. So here we have a datagram in the nth set arrives to the nth router. Basically, the router sends an ICMP time exceed message back to the source, which is going to be type 11, code 0. This means that it may include the router IP address, which allows traceroute to show hop on screen. And then when the ICMP message reaches the source, the program records the runtime trip for each probe. And these measurements help the user understand latency and give an estimate of every hop. So if we see these values per hop, it gives us a more stable estimate. So here what we have is the initial host is going to send 3 probes. That's with a round time trip of 1. and this is considered as hop 1, which is your local router or your gateway. So it sends 3 probes so you can compare the timing variation. If there's inconsistencies, if there's a high delay or packet loss, the first hop will reveal it. And then we do a time to live of 2, and we send those as well to the second, which is usually going to be maybe an edge router or an ISP router. And again, these 3 probes are being sent, and then 3 replies, ICMP replies, come back with their timings. So this helps to spot delays if the message begin to have delays across the path. And then you can see another sent being happening here. So and eventually one of the UDP probes reaches the actual destination, and the destination does not have a service running on a random high number of UDP port traceroute uses. So because of that, it would send back an ICMP port unreachable message, which is going to be a type 3, code 3 message. And once the source receives this final ICMP message traceroute, it knows it has reached the end of paths and stops. So just again, a comparison between ping and traceroute. Both ping and traceroute are going to be built on top of ICMP, which is the protocol that is responsible for reporting network issues and providing simple diagnostic information. So ping is the simplest tool. It would just send an ICMP echo request to a destination and waits for ICMP echo reply. This just tells if the host is reachable and how long it takes for a round time trip. Traceroute works differently. It sends UDP or ICMP probes with increasing time to live values. And then each router that discards a probe and returns an ICMP exceeded message, this message reveals that, hey, this is the identity of the hop, of every hop on the path. So ping answers connectivity and latency. How can I reach the destination and how long does it take? Traceroute answers what path do my packets take and where are the delays happening. So both tools are going to depend on that protocol, the ICMP protocol, but they use different message types and serve different purposes. Here's a figure that I was messing with today and incorporated a figure. You can do this kind of on your own time. Here, my name is the user, and I was pinging Amazon. So we know that how ping works is going to be basically send an ICMP echo, and it will get a reply when or if the host is reachable. Sometimes you will get these where it says request timed out, and then you have a final summary that shows what has happened, how many packets were sent, received, and lost. So this example shows when a ping fails to reach a destination. Okay. See here, we have the source, which is me. I'm sending 4 echo requests to the server behind Amazon, and none of them returned a reply, which caused a timeout message for each attempt. So the summary here at the bottom shows that we have sent 4 packets, and 0 were received, and that results in 100% loss, as we can see here. Now, a situation like this can mean several things. We know Amazon is a big company. It does not mean their host is down. So the several things that we can kind of like draw or conclude from this is that, one, yes, the destination might be down or reachable. Could be there's a firewall or IDS that is blocking the ICMP traffic, and some servers will not choose to reply to ping for security reasons. So even though here we saw that the ping has failed, the server might be fully operational, and it is fully operational for something like Amazon, unless that it is their server is down, their AWS server. Okay, here's an example of ping, of traceroute, and we know that traceroute works a little bit different from ping. And instead of checking simple reachability, it discovers every router on the path to the destination. Okay. And it sends probes with the time to live values, which identifies the router. Here, so we have pinged Amazon here. It's going to give you the number of maximum hops. Every time I usually work with traceroute is over a maximum of 30 hops. So usually the maximum would be 30, and it does not necessarily mean it always will be 30. Sometimes it could be 10. 15, depending on how long it will take or how many hops are needed to reach that host. Okay. Um, it sends a probe with a time to live that increases one hop at a time. So each router discards the probe and sends it back with the ICMP exceeded message at the router. So here we have the number of hops, we have the router IP address, and the runtime chart for three. And you see that some of them are request time down, meaning that at this specific hop, for example, for 20, that server did not want to reply because they either have a firewall that is blocking their request or not. Although we have here some like hop 6, they specify the IP address used, and this is by the DNS server that is built in with this organization. And those three probes, it gives you the time for them to avoid inconsistencies. Okay. So when you trace route something something big like Amazon, you're gonna see big number of hops, meaning that you are reaching many kind of when we talk about the general outline or the overview, you're gonna see many ISPs, backbone routers, and regional transit points. Okay. And the same thing happens with traceroute. It does not mean that the host is unreachable because of these requests timed out. Okay, now we move to our last kind of subject of chapter 5, which is the network management configuration. Okay, so we'll look at devices, how they are monitored, configured, and maintained in real networks. So the main things that we will cover is SNMP, netconfig, and Yang. And Yang is going to be the language that is used by the network configurations. So this is how we can manage routers, switches, and all other network equipment. So the idea is that we want to start and identify what a network management is. And basically, network management is focusing on keeping a large network community or network and infrastructure or topology running properly. So a modern autonomous system, AS system, or network would have like contains 1,000 of hardware and software components that all have to work together. And this is just like under the other complex systems such as airplanes, power plants. Networks need consistent monitoring and configuration and control. So without active management or these mechanisms, the system would drift into a failure or degraded performance. Okay. So this definition gives the full picture. So network management um, involves deploying, involves integrating, coordinating all the hardware, software, and people needed to keep the network healthy. So includes kind of tasks like monitoring devices, testing performance, configuring equipments, and troubleshooting issues. So the goal obviously is going to be to maintain the best throughput, the best performance or quality of the given network while keeping operational costs as down as possible. So there's going to be three main components that are going to be involved in network management. And we have a collection of routers, we have switches, and we have end hosts that form the managed network. And we know that every device in this given image here needs to be configured. We have status for it, and we have operational behavior that must be controlled and monitored. Okay, so this is kind of like a typical environment where multiple devices connect and interact. So the first component that we would have is a managing server. So the managing server is going to be kind of like the brain of the network management system. It runs software as well, used by the network admins to monitor and configure devices. And also humans stay in the loop through the server since all management actions flow through it. Okay. Also stores the main database, the Active Directories, that keeps any configuration information and any collected data. We have the devices, obviously, but we have agents for those devices. So each device in the network becomes a managed device. So it would support configuration and send back monitoring. And these devices are going to run a small software, obviously, that communicates with the server. And the agent is gonna gather anything statistical, expose any configuration or to respond to queries, from the server. So this allows the server to have a kind of an overview of everything, every device, and to manage everything in a consistent way. We're also going to have data, and this is going to be the key thing that is being exchanged between the server and the device agent. So this includes kind of like anything like the current device state, any data, any logs, performance metrics, and operational statistics. So this data is what is managing the managing user uses to make decisions and adjust its setting based upon. We also have the network management protocol, and this, as you can see, the arrow shows the managing server communicates with each device, and they control each device here. And the network management protocol, it defines how the server would query devices, retrieves data, and sends configuration updates. Similar to like HTTP requests and HTTP replies for that given server, you have to have a network management protocol that is being used. Okay, so devices would only also use that protocol to notify the server about events or problems. And this is where we talk about SNMP or net config. And this is how this two-way communication works from the administrators to the entire network to form a central point. So network operators' approaches to management, we have several ways before we dive into netconfig and the SNMP. So the first thing we have is CLIs, and this is one way the operators can interact with the network. And it's actually the traditional way where the operator logs directly into a device, usually over SSH, or types commands hand by hand. So it does give full control, but it does consume time, and it does not really scale well when we have a device where we have multiple devices and every one of them needs to be configured individually. So then we move to SNMP/MIB. So this moves beyond manual work by managing a server to query the devices automatically. So every device is going to maintain a management information base, MIB, and that is called, the MIB that we see here. So SNMP/MIB work together. So this is going to store any configuration points, operational states. So the managing server would use SNMP as a protocol to read or update the entries in the MIB, okay, to update that directory. The directory is going to be the MIB you can think of. So SNMP became very supported and widely used, but it still has a limitation where it focuses on device by device operation rather than the full network. There comes netconfig/yang, and this is kind of the most that is modern today, and it is more abstract and network-wide holistic. So it scales to large networks. That is netconfig as a protocol. Yang is going to define data models that will describe configuration and operational data that is in a consistent format across different vendors. So netconfig or CONF uses these models to push configuration changes and retrieve state from the devices in a reliable transactional way. So this makes that the device configuration and network-wide automation is easier and compared to both command line and the SNMP with the MIB. So let's talk about SNMP first, and this is the one that focuses on only one device. It's not really the protocol that is heavily used and modern today. So we here have a managing server, as we said, and we have the devices that have agents, and those agents would be queried by the server to send information back to that server or the admin. Now, there's two ways to convey MIB information commands. So the diagram that we have a basic architecture here where the server communicates only with the agent. So the first model or the first way is just basically going to be a simple request and response interaction. Okay, so the request and response, this is the mode that the managing server initiates all communication. The server would send an SNMP request to a specific MIB values from a device, and then the agent on the device processes the request and sends it back with the requested data, similar to an HTTP request and replies. Like an HTTP request meaning get, like a get HTTP request. So this model works well for polling or routine monitoring and maybe on a time-to-time status collection. And there's the other way, which is kind of like trap mode. And trap works the opposite way. So instead of waiting for the server to ask information, the device sends a message whenever an event occurs, whenever a trigger happens, or whenever there's something that needs to be sent to the admins. So the trap messages will allow the admins to react quickly or change such interference, drops, threshold alarms, or unexpected behavior. So a trap kind of gives the server real-time alerts without consistent requests. So most SNMP deployments use a mix of both, and that's going to be just based on the event or a typical behavior of the admins. The message types that would be included in the protocol, the SNMP protocol, and these are widely used during the network management. We have the first, which is get request, get next request, get bulk request, and these are all three that are sent from the manager to the agent. Okay, and they want to retrieve data from the MIB. So we'll talk about the first one, get request. It walks through the MIB sequentially. Get bulk request is retrieves a larger block of data efficiently, and yeah. So we move to set request, and set requests are also going to be sent from the manager, and it's used when the manager needs to change a configuration value or update a MIB variable. Response, this is going to be a message that's going to travel in the opposite direction. So this is going to be a message that is sent back from the agent back to the server. And finally, there's the trap message. And as we talked about, this is kind of the one way that the agents would have some sort of trigger that would send a message back to the server automatically. Okay, so these are the messages that would support both requests and replies with the SNMP protocol. So for the format, and this is really going to depend on the message types that we have, and the message types that we are talking about are here. So the messages types from 0, where you can say 1 to 3, 0 to 3. This is going to be the format that is going to support that. So the top structure here we have represents messages from 0 to 3, which includes get next, and get bulk request. Yeah, those are the first three messages and response. So anything from here to this here, trap is not included. Okay, so messages first begin with a PDU type, and this is going to be followed by a request ID, the error status, and the error index, and then the header comes in with a list of variable bindings like name and value and other things. So this is the format that is used, or kind of like the structure for normal requests operations between the manager and the agent. So let's look at trap. And trap represents anything that is a message which is type 4, and that is related to trap. So trap flows from the agent to the manager to report events. So the header here, the trap header we have, is going to include fields like, obviously we have the PDU type still exists in both. But we have the enterprise identifier, agent address, which helps identify the device that is generating that message, trap. They have a trap type and a specific code to give more detail about the event that occurred. We have the agent also. We have a timestamp, yes, of the given message. We also have a name and a value. So timestamp is going to help to let the manager know or the server know what event took place. Okay. We'll talk a little bit about the MIB that works with SNMP, the Management Information Base. And this is the Active Directory, or you could say the database of a managed device. So it stores the device data and some cases portions of its configuration. So this includes things like counters, interface status, protocol statistics, maybe state information the server depends on. So all this data is going to be organized in a place where we call it the MIB, and every device might support multiple models depending on the feature. So and there's going to be hundreds of models and there's many vendor-specific MIBs that have been made, and there's actually 400 modules that are defined in the RFCs. So every one of those models are going to provide a consistent structure so that the managing server can understand the device data regardless of the vendor. We have structure of management information, SMI, and this is going to be you can say, the data definition language that describes how MIB objects are named and typed and structured. So it ensures that every MIB object has a unique identifier and follows something that is consistent, such as these counters, integers, and sequences. So without the SMI, the SNMP system would not be able to interpret the MIB values in a standard way across the devices. Here's an example of MIB variables for UDP. So this table we have here shows actual real examples of MIB variables associated with the UDP protocol. So each object has its own, each one of those objects IDs is going to have its own variables like the name, type, and comments. Okay, so for example, this object ID, the first one, UDP in datagrams, counts all retrieved or all received datagrams. UPN, no ports here, counts datagrams with no listening application. UDP errors, for example, here counts all various deliveries issues. And I think we have here the UDP table, for example, is a sequence where the device maintains one row for every active UDP port. So these values would allow the managing server to monitor the UDP behavior and diagnose issues at the device level. So before we dive into the next protocol, which is going to be netconfig, just to give you an analogy that sums up SNMP, human analogy, as you can think of like an analogy of a hospital nurse and patients. So the managing server is going to be the nurse station, and the nurse station is going to keep track of everything that is related to the patient vitals. It has charts, tools to check on everyone. And this is going to be the managing server that oversees the whole network. The devices with the agents, you consider those as the patients. Every patient is like a network device. They have vitals, health data, and special conditions that need monitoring. And these vitals are going to be like the device MIB variables. And then we have the SNMP agent, which is the patient monitor, where every bed has a monitor that collects patient heart rate, blood pressure, and alerts. And this is going to be the actual agent that's running on the device that collects the operational data. And then request response mode. This is one of the response mode that we have where the nurse actually checks on the patient on a time-to-time basis, asking the patients how they're feeling, if they're okay, if they need anything. So this is the patient monitor responds with the exact number. So this is the get request and response method that works with the SMP, because we said there's two ways it can work. Set request or nurse adjusting medication settings. So if something going wrong, the nurse can change the dosage or adjust the oxygen level. So this is like the request where the server updates device configuration. So set request that we talked about. The trap mode is going to be that sudden trigger where if the patient would drop, has a heart rate drop, the monitor would beeps and alerts the nurse. This is the trap mode with SNMP. So we move to net config, and this is going to be the protocol that is highly used today. And we will talk about how it works. So net config, you can think of it, the goal of it is going to be the same as SNMP, and its goal is to actively manage/configure all devices in a network way. So the difference between them is that SNMP focuses on polling and simple updates, where netconfig is built specifically for configuration management at scale and for higher networks. So the main idea is to give operators a reliable and structured way to push changes across many devices, not just one. We'll talk a little bit about the operations between the server and devices. So netconfig operates through communication between the server and each managed device, similar to SNMP. With netconfig, the server can retrieve configuration data, modify it, and activate new configuration on the device. One of the important capabilities, or you can say features, is atomic commit. And this means a group of configuration changes across multiple devices can be applied in one single action. So netconfig also allows the manager to query operational data and statistics similar to SNMP. And then devices can send notification to the server, or the server stays informed about the events without consistently polling, similar to the trap mode that we have. We have the RPC, remote procedure called RPC, and this is what netconfig will use. Basically, where the manager sends commands and the device executes them well-defined operation. So all the messages of the netconfig protocols are encoded in XML, and that allows them to follow a strict structure defined by Yang models. So we'll talk about Yang models in a little bit. The protocol also is secure and reliable because it runs over TLS, so it ensures the integrity and protection of the configuration data is well kept. So this diagram shows basic initialization, maybe exchange and close between the server that we have on the left. It's going to be the managing server, and these are going to be the devices that have agents that kind of have overview of the data. Now, keep in mind, it's similar to HTTP. HTTP, I think, 2 or the variations or the newer advanced of HTTP versions where the sessions are persistent, meaning that it is not closed until all exchanges happen, and a session must be established first. Okay, so the first thing that is the netconfig session is going to be the initialization phase. So both the server and the agent send a hello message to each other, and the hello is going to advertise their capabilities, such as netconfig features, Yang models, and transport options. So this is going to allow both sides to understand what features the other supports before exchanging the messages. And then we have RPC messages, request, and kind of applies. So once the session is now active and established, the managing server will start to kind of have transfer messages. So each RFC is going to represent a specific netconfig action, maybe such as retrieving configuration, modifying, or activating new setting. The device always would reply with an RPC reply, and this is the message that confirms the result or the requested data. Now here, devices can also send notifications message without being prompted, meaning they notify the server about events such as changes or some sort of alerts. And this phase continues as long as the session stays open. Obviously, there's going to be a point where the session is closed, and this is where the server is finished managing the device. It terminates that session. So this is going to be done through closed session, and ensures that resources are free and no longer operational. So now for any update or any for request, a new session must be established. We'll talk about a little bit of the operations that managing server uses when interacting with the devices. We have first git config, and git config is going to retrieve all parts or a given configuration. So a device can have multiple configuration. And this is going to be like running a setup or running a startup or configuration, the database, or lets the manager read any of them. The Git is going to be more general. It retrieves both data and operational states, such as interface counters, routing information, or system statistics. Edit config is usually used to have some modification, so it includes some modification on the device. So after we send the change, that modification change, the server is going to reply with our RPC reply or OK. That means that both configurations or that message has been accepted. Okay. If there's an RPC error, it means there's something that needs to be changed. So it's some kind of like rollback that is going to be needed to be redone by the server. Lock and unlock are going to be allows the server to lock a configuration data store so that no other managed system, such as netconfig or SNMP, or even command line, can change it without change it during a critical update that prevents conflicting edits. Okay. And lastly, we have create subscriptions and notifications. This supports driven behavior, like where the manager subscribes to a notification from the device, and the device, once it sends the notification, that manager or that server would have important details or important events. And this provides real awareness and consistent requests that are being sent back from the agents. So this is an example of a netconfig RPC message, and that is written in XML. So it shows how a managing server is going to send a structured configuration to change configuration change to a device. So we walk through the important steps or maybe the important parts one by one. So the first thing that we have is the message ID. This is going to be uniquely different for each request. This identifies the request that we have made. So the device uses the ID to match the RPC with the correct reply. We have edit config, and this is an element that tells the device, hey, this message is meant to modify the data. So this is one of the main netconfig operations that are used to update the settings. We have running slash, and this is going to be the target data store. So the target here or running here, the target block that we have is going to specify the configuration data store is being changed. And that specific line, the 6th line, which is running, means the active live configuration on the device. And here we have a configuration of the MTU. So here we have the this specific block, and line 11 talks about this is the config section that contains the actual data or configuration that are being pushed on. This example is to update the MTU of an interface Ethernet from 0/0 to 1500. So XML is a way that we can keep structure so that ensures the device interrupt the change consistently and safe. Here's an example of the human analogy of net config. And that kind of gives you an example. So we have a contractor and a blueprint system. And basically, the managing server is going to be the lead contractor, where they oversee the whole project and they coordinate work, make changes, ensure everything stays consistent. The managed devices is going to be the rooms in the building. So we have every room has wiring, lights, or some equipment that needs updating. So these rooms represents the network devices or the endpoints. The Yang models, which we will talk about next, are the official blueprints. So instead of the managing server guessing of using handwritten notes, the contractor relies on official blueprints that describes the room in a standard way. So these blueprints are going to be the Yang models that define data structure. We have RPC, net config RPC. This is a formal work order. So this is where contractor wants to update something. So they list exactly what needs to be done. So this is the message that we have seen. That is the work order written in XML message of part of net config. We have edit config. This is going to be a change request. So this is going to be something that contractor will say change the light in room 203 to LED. So this is similar to edit config where we are updating specific settings on the device. Atomic commit all or nothing, where we know that this is kind of the feature that net config has. And for example, if the contractor wants to update multiple rooms, they can request that change to be made to everything. So this is the net config atomic commit. We can push an alert or a trigger to all devices on a given network, not to each solely individual device. Notification, which are atomic alerts from the workers. And this is something that is typical where if something happens like a leak or short circuits, the workers notify the contractor without waiting for instructions. So those are the net config notification messages, and we know how the users or the users are managing the web servers can subscribe to these notification messages. Secure session is going to be the way that the integration that works between the server and devices, where TLS is used. So in the idea here, we are using a private meeting room where all conversation happen between the contractor and the workers. This is the config running TLS. Lastly, we talk about Yang. So Yang is the data modeling language that netconfig relies on to describe configuration and operational data. So it defines structure, also syntax, and the meaning of the data that in a consistent way across the devices. So it includes also built-in data types, like similar to SMI, which was provided for SMMP. So XML from Yang description. So from a Yang model that we have, a device can automatically generate XML documents, right? And that describes capabilities and data structure. So this allows the server to understand exactly how to format the config messages from that device. So it removes kind of like the guesswork and ensures there's some sort of interoperability between the different vendors. And here you see how each device can kind of like generate XML document or XML data. And this is going to be basically Yang generated. So on the right here, we see that the netconfig RPC messages follow Yang structure. So this ensures that every message is valid and it matches the schema that's defined by the device. Okay. So netconfig depends on this Yang generated structure to interrupt the configuration changes correctly. Lastly, we have constraints and validations. So Yang defines constraints and rules relationship between the data fields. So these constraints help ensure that netconfig configurations is correct and that is consistent before it is applied. So this kind of reduces the errors and prevents invalid configuration changes from reaching the device. So back to the blueprint for a building, and give you a human analogy. Yang is going to be the blueprint, and this is going to be the official given blueprint of the building. Net config carries out the instructions, maybe modifications, orders, but it only follows what the blueprint allows, which is Yang. The built-in types are architectural blueprints that standardize symbols for doors, electrical outlets, water lines, and so on. XML output, which is going to be a Yang model that can generate any XML description of the device. This is like printing the official blueprint for the contractor. We have constraints and configuration changes. So constraints in Yang specifically are going to be like safety rules and codes that are going to reduce the errors. So in the idea of buildings or the contractors or blueprints, those are going to be codes to ensure that structures are safe and do not violate regulations. Configuration changes is to modify the blueprint correctly, or when a contractor needs to update a room, they must follow the structure that is there. So this is it for the network layer, and this is the general roadmap that we have all went through for today and the past couple of weeks where we spent on. So we gave an introduction of the network layer from a control plane. Chapter 4 was about the data plane. This is more about routing algorithms. So we talked about link state, distance vector, and much more. So just to wrap up kind of a little bit to talk about everything that we have covered in kind of one slide is, yes, we have learned a lot from the network control plane section. So we covered a lot of topics and built kind of a picture of how networks are making decisions, routers, and those routers are making those choices and stay manageable. So we started with different approaches to control the network. We talked about a traditional way approach where each router makes its own decision. Well, we talked about SDN, which gives us a logical way, kind of a big point of view, a centralized control of the whole network. We explored routing algorithms like link state or distance vectors, and we saw how they appear, and we talked about OSPF and BGP. I mean, the OSPF is used internally, locally for the inside the autonomous systems, and BGP is used externally for the communication between the autonomous systems. And you know that why we need to have two different algorithms, or we need to know why we section the given network to different autonomous systems. So that is very crucial and important. Okay. We talked about SDN controllers, and since it's open source, we talked about a few implementations that are in practice and known, ODL and ONS, and how they implement similar to the idea of self-certified networking, but they are like kind of like configured with other features that are being used. Today, we talked about ICMP and tools like ping and traceroute that understands how devices communicate and diagnose paths. And then finally, we talked about network management. So we talked about what is network management, the first protocol with using to handle network management, which is SNMP. We talked about netconfig and Yang, and how these operators can monitor, kind of make changes and maintain devices at scale. So we covered kind of like a chain from routing decisions to network configuration and device management. So that is all what we have for today. So this is, as I said, this is our last lecture. So next week, so you have this weekend, and Monday is going to be our final exam. Sunday you have assignment 3, which is due, just to remind you. Basically, the final exam is going to be similar to the midterm, similar to the assignments that you have seen in terms of format. And the week after that, we have nothing to do. And just lastly, just to complete the SPIs, as I said in the beginning of the lecture, which is really important and highly appreciated if you could. And there's extra credit that is involved. And lastly, for the students, whether you're graduating this semester or for the ones that are still have a couple of years left, I just want to wish you the best in your future academic career or your industry career, wherever you are heading, if you're continuing graduate school or working somewhere. And I'm going to be teaching courses in spring. So I think most of you I will see in spring. I think there's a couple of students that reached out and are going to take my classes next semester. So it'll be good to see you guys. And I hope that you guys enjoyed the class, the structure, and everything was organized well. And yeah, that is it. So I wish you all good luck on the final exam and wish you a happy weekend as well. Okay, so enjoy your holidays and your breaks. I will be also, office hours will be available this week, next week. So any questions, stop by, email me, please. And that is all. Okay, so you guys are all dismissed and have a good day. Thank you, Ian. Thank you.